My name is Thomas White. I'm an associate professor at the University of Nevada in Reno, and I work on what's called warm dense matter. And this is the kind of state of matter that is found inside planets, in fusion reactors, and in material science as well, like industry and processing things. Because of the high densities and the partial ionization of the systems, the warm dense matter samples that we create are often at extremely high pressure, which means that they don't last very long, so maybe 10 nanoseconds, and they are opaque to visible light. So you can't really use any optical diagnostics or anything like that to investigate them. You need to have a free electron laser. Free electron laser is essentially a 3-kilometer long X-ray laser where they accelerate electrons to very high speeds, pass them through an alternating set of magnets called an undulator, and then some X-rays come off from the Bremsstrahlung radiation. So it's an extremely great tool to create a very high brightness source of X-rays that you can scatter off of your dense matter. And some of our best experiments that we've been running recently at LCLS, a free electron laser in SLAC, and at the European XFEL, we're able to scatter X-rays off the target and see the individual motion of the ions. And we can measure things like temperature, we can measure things like sound speed, and we can even try to get at things like viscosity and diffusion in this way. One of the fun things about taking a $1 billion laser that no one else has access to and firing it at like an extreme dense plasma that no one has ever done before, you'll typically find something that no one has ever seen before. And so we go from trying to answer very simple questions like, is this matter going to be a solid or a liquid at these kind of pressures and densities and temperatures that we're going to reach? And so you can use these kind of ideas to help inform models of planetary interiors, like how a planetary interior is going to behave as you go from the outside of the planet down to the center of the planet. That's very important if you want to answer sort of questions about, can this planet generate its own magnetic field through dynamo to support life, all the way down to more mundane things like industrial processing of materials and how can we make these processes more efficient. And then so on top of those basic ideas, we can try to answer the more complicated ideas, viscosity, thermal conduction, and then you can maybe try to answer questions like, how long does it take a planet to cool down? Does it take 100 years? Does it take 100,000 years? And so we can use these to build models of exoplanet evolution and things like this. My advice to students thinking about getting into plasma physics is absolutely, you should jump in. For me, it's been a fantastic field. I like that it's typically small teams working on things. There's room to make a name for yourself. If you've got a great idea, you can be a PI and you can lead that and you can become like famous. You're not a small cog in a big machine. Like you can be integral to the science. The other thing is, this is the perfect time to get into plasma physics. The recent revolution in startup companies, in fusion, and the money pouring into this field right now, there is no better time to get into plasma physics and fusion.